In the last section, we talked about some mole conversions. So taking from mass and converting it to moles, and moles converting it to mass. In this section, we're going to talk about aqueous chemistry. So what do I mean by aqueous chemistry? So aqueous chemistry just means that the solute is being dissolved in water. In other words, the solvent is water. On this topic, we can talk about a few things. So firstly, electrolytes, next solubility, and lastly, we'll talk about some reaction types. And within this conversation, we'll also talk about some solution stoichiometry. So the first thing, let's talk about some terms. And let's talk about ionization. So let's talk about dissociation and ionization. So an ionic compound dissolves in water. The ions and cations are separated from each other, and this we call dissociation. And this can be for either salt compounds, something like sodium chloride, or this could be for strong acids, strong bases, or even weak acids and weak bases. Okay, so if we have ions that are separating from each other, that's known as dissociation. So let's take a look at a few examples. So here we have sodium sulfide. Okay, so if we break that into ions, we know we're going to end up with Na plus and S2 minus. And notice here that since we have two in the compound, two sodiums in the compound, we'll end up with two sodium ions. And the same thing is true for the example below. So here we have potassium sulfate. Okay, so notice that here we have a polyatomic ion, but we're still going to break it into ions. In other words, we'll keep the polyatomic together, but we'll break the compound into ions. So here we end up with potassium ions and sulfate ions. And again, notice we have two potassium, we end up with two potassium here. We have just one sulfate, so we only end up with one sulfate as an ion. Okay, the last one, sulfuric acid. So this is an example of a strong acid that dissociates completely. So again, we'll break it into H plus and SO4 2 minus. Okay, we have two hydrogen in our compound, two hydrogen atoms, and then again, just one sulfate. So we also call this ionization. So when a compound, or in other words a solute, dissolve in water to form ions, the process is also called ionization. Okay, so the act of them separating, that's dissociation, but the act of them actually forming ions, that's known as ionization. So similar terms, but a little bit different meaning there. Okay, so what about miscible, or dissolving? So on the left, we have a sugar molecule dissolving. So sugar is a polar compound, relatively speaking, and therefore it can dissolve into water. So here we just see some water molecules sort of aligning themselves with some of the poles in the sugar, and that causing it to dissolve. So we would call that dissolving. Okay, and generally when we talk about liquids, we'll talk about whether they're miscible or non-miscible. Okay, so an example of a non-miscible liquid, sorry, that's kind of a hard word to say, would be oil. So I think in terms of mixing liquids, sometimes it's easier to think about the things that don't dissolve or aren't miscible. So an example here is oil. So we all know that oil and water don't mix very well, or at all. Okay, so here's an example of oil floating on top of water. So this would be known as non-miscible. Now, if we have two solutes, or solute and a solvent that do mix, let's say an alcohol and water, the alcohol will be known as miscible, or the two liquids would be known as miscible. Okay, so when compounds dissolve in water as molecules, we see that the compound is miscible. And generally, again, we only apply this to liquids, but it's true for either solids or liquids. But generally speaking, this is only talked about in terms of liquids. So an example is sugar and water gives sugar water, of course. But notice the important thing here. Ions are not formed. Okay, so we're not forming ions. That's the important thing here. If we were forming ions, this would be ionization or dissociation. Okay, but we're not forming ions, so the molecule, in other words, is the same going into solution as it was before it went into solution. Okay, so what about electrolytes? So what exactly is an electrolyte? So we can break them into three categories. These are strong, weak, and then we also have non-electrolytes. So a strong electrolyte, so this is a chemical substance that ionizes completely into their ions. So something like sodium chloride, for instance. Examples of these would be soluble salts, strong acids, and strong bases. And one way to detect a strong electrolyte is that it can conduct electricity. It conducts electricity quite well. Okay, what about a weak electrolyte? This is a chemical substance that only partially ionizes into its ions. Example here would be weak acids or weak bases, and they can still conduct electricity, but poorly. So this would be conduct electricity well, whereas weak electrolytes only conduct electricity poorly. And then if we have a non-electrolyte, so this is a chemical substance that dissolves in water, but not as ions. So that the sugar is the best example of this. That's commonly in our common knowledge. Okay, so they do not conduct electricity. So they do not conduct electricity at all. Okay, so sugar, if you, we'll talk about that in just a second. But these are polar substances such as sugar or alcohols. Okay, so in other words, electrolyte is something that you add to water and it breaks into ions, either very well or very weakly. So I mentioned that a good way to spot electrolytes is by checking if they conduct electricity. So here we have two examples of the same setup. So on the left, we have a light bulb connected to two electrical poles, which is connected to a battery, and the same thing on the right. So we're going to assume that the water inside of the beakers, and both of the poles are submerged in water. And we'll assume that that water is completely deionized. In other words, without the addition of some ion, it would not conduct electricity. So let's look at what happens if we add salt to the one on the left and sugar on the one on the right. And obviously you can see that the one on the left, the light bulb is lit up. Okay, so that means that the salt is ionizing. This is just table salt, which we know is sodium chloride. Okay, so we see that's lighting up quite brightly. So we would probably say that this is a strong electrolyte. Whereas if you look at the one on the left, we've added sugar. We notice that the light bulb is not lit up. Okay, so that would indicate to us that this is a non-electrolyte. So what's the difference? Okay, so the one on the left is our ionic compound. So our ionic compound dissociates into ions when they dissolve. So notice we have individual chloride ions and sodium ions breaking off into the solution. So you can see they're sort of getting surrounded by the water molecules, where the negative the negative part of the water molecule points toward the positive ion, and the positive part of the water molecule points toward the negative ion. That's not so important right now. What is important to see, though, is that, so this would maybe be an example of a sodium chloride, where we have Na plus and Cl minus. That was kind of what I was going with in that analogy. But what we see is that it's breaking into ions. That's the important thing to understand here. Whereas if we have something like a sugar, this would be a molecular compound, so does not dissociate into ions when they dissolve. So ionic compound versus molecular compound. So the only thing to remember there is that ionic compounds split into ions, and molecular compounds do not. So ionic compounds would be electrolytes, molecular compounds would not. Okay, so how do we know if we're going to form a solution? Or how could we predict that? Well, for a solution to form, the solute and the solvent must have similar polarities. And we use this phrase, like dissolves like. What does that mean? So nonpolar things dissolve polar things. Nonpolar things will not dissolve in polar solvents, whereas polar solutes will dissolve in polar solvents. And likewise, polar solutes will not dissolve in nonpolar solvents, but nonpolar solutes will dissolve in nonpolar solvents. Okay, so like deserves like. Okay, so there has to be an attractive force between the solute particles holding them together. So when a solution forms, let me go back to that for a second. So remember that there are attractive forces between the solute particles holding them together. In other words, if I have sodium plus, Cl minus, I know I have an ionic bond holding those together. So what happens when we form a solution? So we have to break the solute-solute interaction and replace it with solute-solvent interaction. So let's read the statement. So the solute-solute interactions and the solvent-solvent interactions must be overcome to form new solute-solvent interactions. So, in other words, we have to break solute-solute bonds and we have to break solvent-solvent bonds to form new solute-solvent bonds. So, In other words, the solute-solvent interaction has to be strong enough to break them away from each other, both the solvent and the solute. Okay, so essentially what we're saying here is down below we have some examples. So let's just imagine these purple molecules or atoms, they make up a molecule. Okay, maybe that's an ionic compound. So what has to happen is we have solute-solute interactions, so represented by the arrows. We know we also have, it's not depicted, but we also have solvent-solvent interactions. And then lastly, we have this. We have solute-solvent interactions, or solvent-solute interactions. Doesn't matter which way you say it. Okay, so in other words, we have to break this bond, and then form this new bond. So that's the three interactions we're talking about. So let's take a look at a real example, so sodium chloride. So here we have an ionic bond between sodium and between chloride, of course. And then what we get from the water, and I've kind of been mentioning this, but we have the partial positive, or partial negative, excuse me, of the water lining up with the with the positive ion of sodium. Okay, and then we have the partially positive part of water lining up with the negative part of chloride, or with the negative chloride ion. Okay, and so now we have this favorable interaction, we have this favorable interaction, and if it's strong enough to break the solute-solute interaction, then we can form a solution. So that's the point I'm trying to make here, that we have to break solute-solute interaction, solvent-solvent interaction, and form new solvent-solute interactions, and they have to be strong enough to break all the other bonds, or at least equal to. Okay, and that's how we form a solution. Okay, so getting into acids and bases. So acids and bases are sort of special versions of ions, essentially, or special versions of ionic compounds. We can kind of think about it that way. Okay, so with an acid is just a molecular compound that ionizes when dissolved into water. And it's a special kind of ionization in that we form H plus ions. So when acids ionize, they form the cation H plus. That's by definition what our acid is. The degree of ionization can vary. So we have strong acids and we have weak acids. And if we have acids that ionize virtually 100%, these are called strong acids. So example, HCl. So HCl, when we put it into solution, breaks completely into H plus and Cl minus. Now, if we have, however, an acid that only partially ionizes, this is known as a weak acid. So if it completely, or virtually 100% ionizes, that's a strong acid. If it's only a small percentage of ionization, that's called a weak acid. And here we have an example of a strong acid. So here we have, here we have H. Okay, sorry about that. Here we have HCl. We know that this is minus and this is plus. They come together to form hydrochloric acid. We put them into solution. The H will break off to H plus, and the Cl minus will break off. In other words, they'll dissociate. And if this dissociation is nearly 100%, that would be a strong acid. So the more dissociation you have, the stronger acid you have. Okay, what about a base? So similar idea here, except bases break into their positive ions. So whereas in the acid we usually end up with a positive H plus and then a negative ion. Here we're going to break into a positive ion, so maybe sodium, and then we're also going to break into OH minus. So if something dissolves into water and gives off OH minus, then that would be known as a base. Okay, so a base is a molecular compound that ionizes when dissolved in water, and when a base ionizes, they give OH minus as in the cation. So it could be any cation, but here it could be sodium, potassium. These are generally common ones, calcium. Okay, so again, just like with acids, the degree of ionization varies. So bases that completely ionize, those are strong bases. Okay, and then if they don't completely ionize or only ionize to a small degree, then those are weak bases. So here we have sodium hydroxide breaking into OH minus and Na plus. That would be a strong base. But we'd also have something like NH3. Okay, ammonia. This combines with water to give us OH minus and H4 plus. So we don't often think of ammonia just commonly as being a base, but actually it acts as a base in water. Okay, so here we have the example of, so here we have sodium, and we'll just represent the whole OH minus with this green sphere here. And if we add this to water, it breaks into Na plus and OH minus. So that's our base. So again, just to kind of rephrase a little bit or go back a little bit. So an acid gives us H plus and an anion. A base gives us OH minus and a cation. Okay, so what affects the solubility of ionic compounds? So this next little section we'll talk about solubility. Okay, so we know that compounds dissolve into solvent. Of course, they're said to be soluble. If something dissolves, it's said to be soluble. Well, if something doesn't dissolve, it's known as insoluble. So two examples. Sodium chloride is soluble in water, where silver chloride is never soluble in water. So this would be soluble. This would be insoluble. Sorry for my handwriting. It doesn't always pick up well. So, what affects the solubility of a compound? So the solubility of a compound can be affected by temperature. So is the solution hot or is it cold? The volume, do we have lots and lots of solvent or a little bit of solvent? And then for gases, we have pressure. So remember that pressure is essentially concentration for gases. Okay, so here we have a statement, even insoluble compounds dissolve, just not largely enough to be meaningful. So when I say silver chloride is insoluble, do I really mean that no ions are formed? Well, no, that's not quite true. But it's such a small amount of ions, we say that it's not meaningful. And you can actually do experiments where you measure the solubility of quote-unquote insoluble salts, and you'll actually find that there is some solubility there. But again, it's such a small amount that it's not meaningful in any way. Okay, so predicting whether a compound will dissolve in water is based on experimental results. So in other words, there's some rules that will tell me, and I have some guidelines that, based on this and based on this, well, I can say, well, this should be soluble, but it might not be. Or I should say that this should be insoluble, but maybe not. And the only way to be sure is by doing experiments. So in other words, if in my lab and I synthesize a compound, or I have a new compound, maybe I've never worked with, say, some silver salt before, and I want to know what's soluble in. Well, I could ask my lab partners, and they may have some experience, and they may know. But if no one knows, all I can do is I can go to my tables, and I'm going to show you the solubility rules in just a second. But I go to my solubility rules, and I say, okay, well, it should be soluble in this, should be soluble in this, but the only way to know for sure is to do experiments, and this is called the empirical method. In other words, we learn through doing experiments, and that's the only way to truly know. So with that said, we do have some solubility rules. Okay, so these rules are just general guidelines. So it's a basis to kind of guide you in the right direction, but they're not set in stone. Okay, but they are backed by experimental results though. Okay, I'm going to show you a couple different versions of this table. Okay, but let's start with this one. So on the left, it says soluble ionic compounds. On the right, it says insoluble ionic compounds. Okay, so they give us some kind of guidelines here. So first one, it says group 1A ions, so this is your lithium, potassium, sodium, etc., and ammonium ion are all soluble. Okay. The number 2 says nitrates, acetates, and most perchlorates are soluble. Next one, number 3, says chloride, bromide, and iodide are soluble, except when paired with silver, lead, copper, or mercury. Number 4 says sulfates are soluble, except those of calcium, and etc. So silver, lead, etc. So that gives you an idea of what should be soluble. But notice here on the right, it says insoluble ionic compounds. Okay, so hydroxides and sulfides are insoluble except with group 1A, so lithium, potassium, etc. Okay, then we have carbonates and phosphates are insoluble except with group 1A. So notice both of these rules kind of point back to this first one. Okay, so this is sort of one style of chart. And this is another. And this one I think is probably the more useful version. Okay, so it says compounds containing the following ions are generally soluble. So we have our group 1s and ammonium. And on the right we have exceptions. So it says when combined with ions on the left, the compound is insoluble. So with our group 1A, notice that there's no exceptions. So if you see something from group 1A, or in other words, your sodium, lithium, potassium, etc. So if you see something from group 1, know that it's generally probably soluble, unless you see an exception somewhere. And here we have no exceptions. Okay, we have nitrate acetates. Again, those are soluble. What's the exception? None. Okay, next I have chloride, bromide, iodine, my halogens. So those are soluble except when what? Paired with silver, mercury, or lead. Okay, so that's kind of how you start thinking about this. So in other words, if I see lead in a compound, even if it's lead chloride, so the chloride might lead me to believe it's soluble, but if I see lead, okay, well I know it's not soluble. Sulfate, generally soluble except when it's paired with silver, calcium, strontium, barium, lead, etc. So notice a couple of things here. So silver chloride, that's a good one to remember. So if you have a silver salt, you might want to question it. And if you have a lead salt, you might want to question it. So that's kind of how you use these tables. Here's some more. So compounds with the following N ions, so OH minus, they're generally insoluble unless what? They're paired with, here's our group 1 again. Okay, and then here's our group 2. Okay, so I have lithium hydroxide, potassium, sodium hydroxide, calcium hydroxide. Those are going to be soluble. And the ones in red, those will be slightly soluble. So your calcium, strontium, barium. Those will be slightly soluble. Okay, sulfide compounds are generally insoluble unless paired with what? Group 1 and group 2. Okay, so hopefully you kind of get the idea here. Then carbonates. So you just kind of go through this and you sort of need to get some touch tones. So again, things like lead, silver, these are sort of your touch tones where, I know group 1 is going to be soluble. So things like that, you can got to get a feel for. Okay, so here's a list of 5 ionic compounds. So what I'd like for you to do is pause the video and using the rules I just showed you, go through these and see if you can decide whether they're soluble or insoluble. I'll give you a few minutes. Okay, so let's take a look at these. So we have 5 examples here, and all we want to know is they're soluble in water or not. So the first one, KOH. So first, let's look at the ions. So we know it's going to break into potassium and hydroxide. And we have to think back to our rules, and for this you could have gone and looked at them. To think to our rules. Okay, potassium. I know there's no exceptions to anything being soluble with potassium. But I know there are exceptions to OH. What I have to remember is potassium an exception to the OH? Well, no, it can't be because there are no exceptions with potassium. So, of course, I could say that KOH is soluble because it contains potassium. Okay, the next one, I have silver bromide. So, again, this is one that should raise a red flag for you. Okay, now I have silver, I have bromide. What are my rules for silver? So, go back in the table and we can check. So bromides are generally soluble. Of course, our halogen compounds are generally soluble, except with silver. Okay, so that right away lets me know this can't be soluble. So silver bromide is insoluble because most bromides are soluble, but silver bromide is exception. And that's because of the silver. Next one, calcium chloride. So I have a group 2 and I have a halogen. Okay, so again, break it into calcium and to chlorine or chloride. And now I have to go back. So what do I know about group 2? If I come back. Let's see. Let's find chlorides. Chlorides. Here we go. Okay, so I have chlorides are soluble, except with silver, mercury, and lead. Okay, what do I have? Silver, mercury, lead? No, I don't. Okay, so it would be soluble because most chlorides are soluble, and calcium chloride is not an exception. Next one, lead. Again, here's a big one. I see lead. Is it soluble or not? But now I have lead nitrate. Is lead nitrate an exception or not? Okay, again, I have to go back to my table. Let's find nitrate. There's no exceptions, not even lead. Okay, so that would mean that it is soluble. Okay, so even though this one is soluble, always think when you have lead insoluble. That's the best way to go. But you also have to think about your nitrates and your sulfates and all these different things and try to remember your rules there. Okay, so this happens to be an exception to what I'm telling you about lead not being soluble. But that exists, so you have to know that. Last one, lead sulfate. You can probably guess based on lead and sulfate. Let's go back. Sulfate. So generally soluble except when paired with what? Silver, calcium, strontium, barium, and lead. Okay, so that tells me that no, this is insoluble. So most sulfates are soluble, however lead sulfate is an exception. Okay, so I think we'll end the video here, but one thing I wanted to say before I end is that these rules, basically you just have to work with, practice, and you have to somewhat memorize them. There's no good trick I can show you aside from just having some touchstones. I also put in the folder, I will link to another video that discusses solubility and using the solubility tables that you might also find helpful. Okay, but generally speaking, these are just things you're going to have to know.